Hey, 8th graders, algebra kids, how you guys doing? Hope you're had a great weekend. Before you get into this new chapter, I want to make sure there's 5 or 6 of you that had a few test corrections. I sent them separately to your assignments, so each one of you has a different assignment. I want to make sure you do that today as well, so you can earn back some points on that quiz. There were 4 of you that already have grades in RunWeb. If you did not get an assignment from me, you're good to go. Okay, some of you have a bunch of questions. Some of you have 1 or 2. I'd just like for you guys to get some points. The word problem question that was on the quiz, I gave everybody, I'm just going to let that one go. I'm going to give everybody problems. Hopefully you saw my review video that went through how to do it as well, just so you know how to approach that. Okay? Today we're going to start chapter 8, which focuses now on quadratic functions. So thus far, we've pretty much been focusing on linear equations, which means it creates a line. These new functions that we're going to talk about are quadratics, and they're going to be in that U shape. So it's going to be in a smiley face or a frowny face, and we'll get into that as we go through our notes here. Okay, this is a lot of stuff. You don't have to write all this stuff down. What I want you to write down is this definition. A quadratic function is any function that can be written in the standard form of y equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. That's a lot of words, okay? But basically it's saying you need to have an x squared in your function, okay? Like I said in the previous slide, this is what our function will look like when it's quadratic, or it might look upside down, smiley face, or a frown. Okay? All right, so here we're going to look at what makes something a quadratic function. Okay, we know that our linear functions before, you had to have a constant change in x and change in y. That was our slope. That's what made something linear. Now we're going to talk about differences between the y values and x values that are called first differences. Okay? And actually second differences for the quadratics. So if we look at this, we have this chart here. When x equals 0, y equals 0. When x equals 1, y equals 1. When x equals 2, y equals 4, because 2 squared is 4. When x is 3, y is 9. And when x is 4, y is 16. So if you look at this chart, you have a constant change of 1 every time you're increasing your x. You're increasing by 1. When you go to your y values, this is a little different. You're increasing by 1, then 3, then 5, and then 7. Those are called our first differences. That's in the first step of the problem. What we're interested in is called second differences. So after we figure out what these differences are right here between these numbers, then we're going to find out the differences between the difference. I know it sounds so weird, but we're going to take and say, well, how far away is 1? You know, if my first problem, I'm increasing by 1, but then I'm increasing by 2, it's a change of 2. I'm sorry, yeah. And then if I'm going from 3 to 5, again, changing by 2. 5 to 7, again, changing by 2. Because this second difference is constant, that means you have a quadratic formula. Okay? So that's what we're talking about here. Make sure you have this jotted down somewhere because it's important to know that. Okay, so we're going to look at an example. Here's a bunch of numbers. We have x's and we have y's. We want to see if this relationship is quadratic. Okay, so we're going to take our x's first and determine if they have a constant difference. And they do. Every time you move from one x to another, you're increasing by 1. So now we can move on. We can continue and see if our y differences, our second differences, not our first, are also consistent. So when I do my y's, I notice that when I go from -9 to -2, I'm increasing by 7. When I go from -2 to -1, I'm increasing by 1. When I go from -1 to 0, I'm increasing by 1. 0 to 7, I'm increasing by 7. These are our first differences. We don't really care about those. We just make sure they're right, but we don't care about them. From here, from these numbers here, we're going to find our second differences. How do I get from 7 to 1? What do I have to do? I have to subtract 6. From 1 to 1, I have to add or subtract 0. Same thing, right? If I go from 1 to 7, I have to add 6. These are not consistent changes. So therefore, we do not have a quadratic. Okay? So let's take a look at another one. Okay, now this one is actually an even easier way. We don't have to even look at numbers. We can look at this equation and hopefully, fingers crossed, because we kind of beat this to death in chapters 5 and 6, actually 4 and 5. This is not a quadratic. This is a linear function. This is y equals mx plus b. Okay, that's the first dead giveaway. The second dead giveaway, the x is not squared. The x is just good old x. Okay, so this is not a quadratic. How about this one? You see this x squared here? Guess what? It's a quadratic. Okay, you really don't even have to do this where you move the x over to the other side, but if you want to, go for it. If you notice, this is x squared, and this 10 is not equal to 0. Remember, our rule said a cannot equal 0. So we have a quadratic. Okay, pretty easy. Okay, so now moving on to the graphing aspect of this. We're going to get into graphing it kind of the right way later. We're just going to talk about a couple characteristics with the graphs. So if I look here, I have a frowny face. Okay, before I showed you a smiley face. So it's either going to be a smiley face like in one of the first few slides, or it's going to be a frowny face like this. We call this graph a parabola. Okay, make sure you write that definition down. The graph of a quadratic function is a curve called a parabola. So right now, what we're going to do to graph this is just come up with enough ordered pairs. That's where we do our t-chart, and we pick random x's, plug it in, find our y's, just like our function machine, and graph those points. Okay, then you connect them with a nice smooth curve that looks symmetrical. These from here, if you were to fold this on the y-axis, you would have a symmetrical curve. All right, so if you look at this function, we have y equals 1/3 x squared. We know that this is a quadratic because we have an x squared. Our a is not equal to 0. We're going to pick random points. Now, I would have picked -3, -6, 3, and 6. And the reason I would have picked those is because then the 3 would cancel out. So keep that in mind. Oh, wait, no, it's x squared. Never mind. It wouldn't necessarily cancel out. I would try and find something that would help cancel it out. So if you plug in these numbers, if you plug in -2 into here, -2 times -2 is 4. 4 times 1/3 gives me 4/3. That's how I get these numbers. We've done enough plugging and chugging for the last 3 years, essentially, that I'm not going to go through each, but I would highly suggest you write these out and show your work. Don't just do it in your head, okay? So once you get your tables, you're going to graph your points. So this might be a little tricky because these aren't perfect numbers. Do the best you can. The point is that you get this minimum point here and then the symmetrical points. Notice how your -2 and your +2 yield the same number. So they're going to be right across from each other. You notice that? Same thing with your -1 and your 1. Okay, so a lot of times you're going to have those symmetrical points. Okay, same thing here. Y equals negative 3x squared plus 1. When you plug these numbers in, this is the result. You plug that into a graph paper, and here you go. Okay. And you plug those points. 0 is equivalent to 1. Negative 1 was equivalent to, or when you plug negative 1 in, you get negative 2. Here you go. That's that point right there. And then when you plug in negative 2, you're actually off the charts. It's negative 11. It's down here somewhere. So this is where it gets a little tricky. You need to kind of estimate based on the first couple of points that you have. If you can get a third or fourth point, I would definitely do it to kind of estimate the way the curve goes. Okay. Now, here's a couple things. This is what I want you to write down, this bullet point right here. A parabola opens upward when a is greater than 0. So that means if you have a positive number in front of your x squared, you're going to have a smiley face. Positive, smile. Okay? When you have a less than 0 or a negative in front of x squared, you're going to have a parabola that opens downward. You're going to have a frowny face. Negative, frown. Okay, that's how you remember that. So for this example here, all we want to do is tell whether the graph of the quadratic function opens upward or downward, and then explain. So notice we have y minus 1/3 x squared equals x minus 3. I want to solve for y before I can determine anything. If I don't solve for y, I don't really have a function, right? Remember? Y is all by itself in a function, and then we can look and see what we have going on. So if I add 1/3 x squared to both sides, I get a new function of y equals 1/3 x squared plus x minus 3. So this is going to tell me a lot. This is going to tell me that this opens upward. It's a smiley face because 1/3 is positive. Okay? And that's all there is to it, to identify it. Okay, so when we go to graph, this stuff is really important, knowing which direction our parabola is going in. How about this one here? Y equals 5x minus 3x squared. Technically, you don't have to move anything around, but to be formal, we flip-flopped the 3x squared and the 5x. The negative goes along with the 3x squared. Okay, because that 3 is negative, guess what? It's going to be a frowny face or opening downward. Okay. The last kind of point here that we're going to talk about is the vertex. So we have a high or a low point in our parabola. That's going to be called our vertex. I need you to write this whole thing down. If the parabola opens upward, the vertex is the lowest point, or it's called a minimum. Okay, if a parabola opens downward, where it's a frowny face, and think about it, it's logical, right? The vertex is your highest point, and therefore you have a maximum. Okay, this is in your book if you want to kind of look it over, but this just kind of just reiterates what I just said. You have a smiley face. This point is your lowest point. That's your vertex, and it's your minimum. Okay, so your vertex is -3, 0. But your minimum number is 0. You also have a frowny face here, which means you have a maximum point for your vertex, and your vertex is 3, 5 with a max of 5. Notice that your max or your min is going to be your y value. Okay, so I have about 40 seconds left of free time on this video, so if I don't finish, there might be a second video, so just keep an eye out for that. Here we go. Identify the vertex of each parabola, then give the minimum or maximum value of the function. So this is a smiley face. Part A is a smiley face. That means we have a minimum, and our vertex is -3, 2, which means our minimum is 2. This one here is a frowny face, which gives us a